Okay, so we are in generalized linear models with examples in R, chapter 2 still. Question 2.9, and so this is a three-parter, so we'll just take them one at a time. Okay, so we are considering simple linear regression that looks like this. We have an intercept and then a slope, beta 1x, and we're going to design an experiment with 5 observations. In all cases, the variance is known to be 1, okay? For each design, x, which is our data variable, in one of the designs, design A, the data we get looks like this. In another one, the x looks like this. And then the third one, design C, x, again, the data variable, looks like that. Okay? So the first thing we're going to do is we're going to write the model matrix, or maybe sometimes called the design matrix, for each of these different experimental designs. Okay, so generically they will all look like this, where there'll be a column of 1s, which reflects the intercept, beta naught, and then the data variables. Okay, so if we just do that for each of them, so here's for A, B, and C, the 3 designs. Okay, and capital X is meant to denote the entire matrix, all of the so not only the intercept but the data variable, and so this is for XA, XB, XC. Okay, so now we're going to compute the variance of mu hat, or maybe called y hat, or the expected value of the outcome given the data. Okay, so so again. The variance of the expected outcome of the data is what we're trying to estimate here. Okay. If you look earlier in the book, then you'll notice that the variance for mu hat is equal to this expression, where the capital letters, again, are matrices, like what we have up here, and then the lowercase x's, actually that should be x capital T. Let me change that real quick. Okay, and then the lowercase ones are a vector. Okay, where the vector here is 1 for the intercept and x for the prediction, or the x value. Okay, the new x value. Okay, so and again, in all cases, sigma squared equals 1. So this guy right here is just 1, so it'll just kind of drop out. Okay, so let's do for design matrix A. Okay, so now in each of these cases, there's going to be this W matrix, but we're assuming that there is no covariance among the parameters or data points, and so it's just the identity matrix, which is just a matrix of zeros with ones down the diagonal. But more importantly, whenever you multiply something by the identity matrix, you just get whatever you had right back. Okay, so we're just dropping that out. So anyway, so the first thing that I do in each of these cases is I matrix multiply what's in the parentheses here. Okay, so when you do that, you get this, and then to take the inverse of that, so if, you can look up how to do that, but with a 2 by 2, it's very easy. You just take 5 times 4. You take the product of one diagonal, 5 times 4, which is 20. Minus the product of the other diagonal, which is just 0 in this case, so it's 20. And so you put 1 over 20 outside, and then you switch the position of this diagonal, and then you make the other diagonal zeros. I know that I didn't demonstrate it here, but if you know what an inverse is already, hopefully that was a little bit of a recapture, or you can just Google inverse of a 2 by 2 matrix, and that will get you where you need to be. But anyway, the inverse should be this, and then we just matrix multiply through the 1 over x, and then again the 1x here, and we should come out with an expression that looks like this. Now the book gives a slightly different answer. It gives this. It gives, instead of 0.2 plus 0.25x squared, it gives 0.2x squared plus 0.25. So I think that maybe the author made a mistake here, because in order to get this expression, you would have to have that kind of this portion right here came out to being 4, 5, and then, well, and then these would be flipped. So I think that, that there was just a mistake in the book. Okay. So anyway, so what's important here is that we come out with this expression that is expressing the variance of the prediction for little x. Okay. So we can do the same thing, and I won't go through the steps anymore. But I'm doing the same thing, right? So I'm just finding the inverse of this middle part here, okay, which in this case is this, and then multiply through, and in this case this is the expression, and then for the last one we come out with this expression, or this expression that we simplify to this. Okay, good enough. So again, you can walk through the math for yourself, and now in the third part here, we are going to plot the variance of mu hat between values of -1 and 1, okay, and then say when each of the different designs would be preferred. Okay, so this code is just taken from the back of the book. This right here actually doesn't do anything, I don't think. I'm going to delete it. Somewhat. Okay, good. Okay, so all that we're going to do is we're going to come up with values for x, okay, and then calculate the variance for the 3 designs. And to do that, we are just, we already found these expressions, okay, and we're going to plug them in here into these functions, okay, and then so now I have a function called var a, and I feed it the argument x, and I've already defined x to be values between -1 and 1, so va is just my function variance a over x, and for b and for c, okay. You'll notice that in the back of the book, they put the expression here that the author derived that I believe is mistaken, and so I've corrected it here. Okay, and well, anyway, so now I go through and I'm just going to plot. I'm going to plot these different variance functions for the different values of x when x goes between 0 and 1, or I'm sorry, -1 and 1. Okay, and then we're asked, when would each design be preferred? Well, a design would be preferred, all else being equal, when its variance is lower than the other 2. Okay, so for instance, here, so between values, let's say of 0 and -1, then design A would be preferred because it has the lowest variance. Okay, but for higher values of x, say about 0.25 and up, then it looks like C, design C. No, what would be B? B would be preferred. Okay. Notice that C is probably never preferred because when it's at its lowest, it is still, well, it might only be preferred around 0, I guess, but it's always above or apparently equal to. I'm sure that we could solve that analytically, but B is maybe, or I'm sorry, C is probably never preferred.